Hello everyone. The project title is Alien Detection and I am Khushi Rathod and Samyak Jain and I are team members. In this project, we are trying to draw lane lines on the images using OpenCV techniques. We are trying to understand the images and draw the lane lines on them using the OpenCV functions. Yeah. Firstly, we are trying to explore the images in the various color spaces. Here, the color spaces that we have tried to explore are HSV and HSL, where HSV is hue saturation value and HSL is hue saturation and lightness. The difference is in hue saturation value, if the value is maximum, then we will be able to observe the image, observe the image. But whereas in HSL, if lightness is maximum, then we'll observe a complete white image. If the visibility of the colors will decrease. So here in this HSL and HSL color space, we observe that in HSL color space, yellow and white are quite vibrant and quite visible, so that we can detect them. Whereas in HSV color space, as we can see that yellow and white we can't observe and demarcate those lines. They are not very vibrant and popping up. So we'll go ahead with HSL color space. Secondly, now we will be masking the images because we want to extract the lanes only. We will set a threshold value and extract only yellow images so that we get a yellow lane line, and similarly we set a threshold and obtain a white masked image. And then we OR those images and obtain a proper mask, yellow and white masked images. As we know that the images that we had chosen were initially RGB color space. They had 3 channels, but here now we are converting them into grayscale images, which does not have 3 channels for further processing. And now we apply Gaussian blur techniques on the apply Gaussian blur techniques on the images so as to reduce the noise and be able to extract the required features only. We can apply Gaussian technique with a Gaussian function available in the OpenCV library. In the first column, as you can see that column, as you can see that the kernel size was taken as 5, and in the second column the kernel size was taken as 11, and the third column the kernel size was taken as 21. So the images are best observed in the 21 kernel size. So we'll go ahead with the 21 kernel size because the noise is very much reduced in that kernel size. Yeah, now as we have reduced the noise, and now we want to detect the lane lines, we apply the canny edge detection method. In this detection method, what happens is when a image is given as input, it will obtain a sketch of that image as output. So yeah, here we will be able to clearly demarcate the lines. So while applying canny edge detection method, a parameter of threshold has to be passed to the function. Here we have passed 50:150 and 1:10 and 1:5 as the threshold values. These threshold values are important to segregate the pixels into strong pixels, weak pixels, and medium pixels. Here, strong pixels are the pixels which are above the threshold value, and medium pixels are the pixel values which lie between the threshold values and low and high threshold values, and the weak pixels are the pixels whose pixel intensity lies below the threshold values. So the weak pixels will not be relevant at all, whereas medium pixels will be relevant and will be contributing to the line detection, whereas strong pixels will be definitely contributing to the detection of the line. So here we see that 50:150 detects the lines very properly and the noise is furthermore reduced, so we will go ahead with the 50:150 threshold value in the canny edge detection method. Once we have detected the lines, the edges in the images, now we want to obtain only lines. So we will apply we want to extract the region of interest from the entire image. So basically, the main idea behind obtaining the region of interest is the camera is always fixed on the top of the car. So we will have an idea of where the lines will be formed mostly on the road. So this is the main idea behind finding this idea of finding the region of interest and discarding everything which is does not come under the area of the region of interest. Here, by mere observation, we have used four vertices whose values are given here: bottom right, and top left, and bottom left values are given here. And we have tried to obtain the we have used quadrilateral as our region of interest and obtained only quadrilateral image. Everything else that does not come into these four vertices will be discarded and will not be processing them further in the images. After finding the region of interest, now we will be trying to find the lines. So as to find the lines, there is a whole transform technique. In this whole transform technique, initially all the images are in the Cartesian plane, but this whole transform technique goes through the pixels and then finds their counterpart in the polar coordinates form, where which is in the form of r comma theta. So as we know that to define a line, only r comma theta are enough to define a unique line in the polar coordinates, whereas in Cartesian form we need slope and intercept to find the lines. So we will be using this technique. In whole transform, it will travels through each and every pixel and maintains an accumulator matrix in which it will vote the pixel which has been counted the most as contributing into the line. Suppose in the first image it is going through the pixels and it goes through a line. So every time it passes the line, it will vote its particular r comma theta value, which is same for any pixel lying on the same line. So the pixel which is voted the most is considered as the line. So this is how we obtain the lines from the whole transform techniques. The whole transform technique returns the r comma theta value of that particular line. And from these r comma theta values, we can form the points and then we can draw the line with the CV2 dot line function in the OpenCV. So here we can see that red color lines detect the left lane line and blue color lines detect the right lane line. And in the end, we have extrapolated the lines. So after obtaining a given line, as we can see that the lines are not fully on the lanes. So what we do now is we use the linear regression technique. We're given few points. It returns the slope and intercept of that line, so that we fit the available coordinates of the line obtained through whole transform into a linear curve and obtain the lines. So in this simple technique in which of OpenCV to obtain the lane lines, we have tried to fit the coordinates we have obtained into a linear curve, and we have extrapolated the lines as seen here at the bottom row. Next, we move on to the advanced lane and detection method. Here, we have used the concept of distorted images and undistorted images to have a better understanding. Have a look at the chessboard. Have a look at the chessboard thing. Here, we observe that the first image on the left side is a bit distorted. It is because given a camera has a convex lens, when lights traverse through the convex lens, there is always distortion, and there is always little more or less errors, and we cannot obtain the images on the 2D plane as we are seeing them with our naked eyes. So we want to convert the distorted image into undistorted pure image so that we get the exact vertex of each and every point on the image. So because chessboard has proper black and white contrast, we can easily find the you can easily find the undistorted vertices, and this is done through the vertices of the distorted image are the image points, and the vertices in the undistorted image are the object points. For a given chessboard, its undistorted image can be obtained by using find chessboard corners function, and then the the values obtained from the function can be fed to the calibrate camera function. Image points and the object points are fed to the calibrate camera function, which returns the distortion coefficients, rotation, and translational vectors matrices, which is again fed to the undistort function in the OpenCV, which gives the undistorted image as the output. Now this undistortion concept is applied on the lane lines images, and we can see that the undistorted image is obtained, and we can also see that on the left hand side, bit side view of the region has been cropped out because of the undistortion of the image. Now we explore these images again in the various color spaces. Here we explore the images in each channel of the color space. For example, in RGB, we examine the images in red channel, green channel, and blue channel. Here we observe that here we observe that in RGB color space, the blue channel detects the yellow line poorly, but HSV color space, the lightness and value channel perform very similar. And also in HSV, the gray component is very dominant. But in labs, L channel is better at detecting yellow and white channel. But labs A component is worst at it, and labs B channel is good at detecting yellow channel. So we will go ahead with the HSL values, HSL color space, and labs L channels color space. Now the next task is to find the edges. Here we use Sobel method for detecting the edges. Here the Sobel method has a inbuilt process in OpenCV which applies Gaussian blur to the images and also detects the lines in the images. Here, while using the Sobel's operator, it uses the Laplacian operator as a method to find the gradient vector that points in the direction of the greatest increase of function, and its magnitude is the slope of graph in that direction. Here, Sobel's derivative in x and y direction is obtained. Uh, then the sum of the squares of Sobel's derivative in x and y direction is taken to obtain the Sobel's derivative at that point. And also, here we are giving threshold values, which helps us in examining which pixel value should be included to contribute in the edge detection, and the kernel size is also passed. Here we use 11 cross 11 kernel size and 15 cross 15 kernel size. Here we can see that we have obtained the images in Sobel's by applying Sobel's operator in the x direction and Sobel's operator in the y direction also. In both the directions, threshold value as 20, 20, 120, and kernel size as 15 into 15 is giving better results. So we will be going ahead with those values. Now we see that as we have detected the lane, detected the edges, lane lines. Now the next task is to remove the noise and obtain the required features only. So here we will, this method differs from the simple lane detection by, because we are taking the, we are viewing the images from a different perspective from that of the camera of the camera of the vehicle that is being fitted and it's fixed. So we view these images from the bird's eye view. There is a function in OpenCV that converts the perspective transform into bird's eye view. But firstly, the first method is to, the step one is to find the region of interest. Here again we use the quadrilateral quadrilateral to find the region of interest, to extract the region of interests by manually examining and giving the vertices of the quadrilateral, and then these vertices are fed into get perspective transform function, uh, which transforms the function into its bird's eye view image. Now the bird's eye view function wraps the provided vertex of quadrilateral and the required destination vertices into the image, which has to be seen as the bird's eye view image. Now, the last column is the column which is showing the bird's eye view image of the respective undistorted images. And from these images, we try to plot a histogram of the pixel values of the bottom half of the image. So now we will see why we need to plot a histogram of the pixel intensities. Here, these pixel intensities that we have plotted on a histogram, we utilize it to detect the lane lines using the sliding window technique. Here in a sliding window technique, the first method is to, first step is to declare a window of, first step is declare a window of required size and width and also define the number of windows we want to use to detect the lane line. Sliding window approach is used here with 9 windows to detect non-zero pixels in the binary image within the sliding window boundary and append it to the, and then we append it to the list of left and right lane pixel arrays. The lane pixels from the sliding window search is then we fit it into a second, the values that we have obtained through the sliding window technique are fit into a second order, second degree polynomial. Now, once we have used the window, 9 windows and obtained the values, these are fit into a polynomial. This polynomial is further used to detect the lane lines. So the first method where we use the window lane lines is called brute force, and second method is called local search. This method is very efficient in detecting the lane lines because here we are fitting the what coordinates coordinates that we have got into a second degree polynomial, whereas in the simple linear detection we had fitted the vertices that we have got into a straight line, a linear degree polynomial. So this is a better method of detecting the lane lines. Yeah, this is a snippet of detection of the lane lines using advanced computer vision method. Next, we have tried to build a convolutional neural network method of VA16 unit segmentation model to detect the lanes. Here, what we did was we created the dataset by utilizing the images of the Udacity self-driving nanodegree program, and the label images are the images that we have got through the advanced computer vision technique and the simple lane line detection method, and we have put the Udacity self-driving dataset images into test images, and annotations images consists of the images which is obtained after applying the advanced lane line detection methods. uh, the dataset consists of 23 images and the corresponding annotations. Here we wanted to predict the two classes. One is binary 0 and binary 1, but it was throwing error when we assigned the number of classes to the VG16 unit model as 256. It was showing an output, but this is what the output that we have got. There but it was an attempt, and we could not successfully succeed at it. It can be further taken up, and this model can be further improved, and a better label image can be obtained. Yeah. Now we would like to show you the video in which the lane lines have been detected. So here it is. This has been done with the sliding window technique method, where we try to fit the vertices that we have obtained to a second degree polynomial. Yeah, this is it. Thank you everyone for your time.